Hello, my name is John Peach, and I'm a data scientist on the Oracle Cloud Infrastructure Data Science Service team. In this module, we will talk about version control systems, what they are, and how they are used in data science. We will review how to set one up and some basic commands. Version control systems are the first concept that I want to introduce in this module. Another name for them is source code management systems. They are a tool that allow you to manage different versions of the code, documents, data, analysis, and other document-like resources. While version control systems were developed for traditional software development, data scientists have adopted their use to manage the analysis that they perform. For example, data science users use source code management systems to track their various versions of their JupyterLab notebooks. It is a great way to manage changes and share with others. There are many different types of repository systems available, such as CVS, Bazaar, Subversion, Perforce, Code Commit, Mercurial, Helix Core, and many more. However, Git is by far the most popular one, and it is integrated into the data science service. Therefore, we'll almost exclusively be talking about Git in this module. Before we get too far, I want to clarify what I mean by code. In this module, I will generally be referring to anything being tracked in a version control system as code. Most of the time, it is actually code being tracked. However, the version control system are commonly used to track data scientists' work such as documents, reports, data collection, statistical and machine learning analysis, and many other work products that they create. A version control system can manage many separate resources. These resources are typically a software application or an analysis. Each resource is stored in a separate repository. Think of a version control system as all the operations that you can perform on a room full of filing cabinets. Each cabinet has a different piece of software in it. In this analogy, the filing cabinet is the repository. It holds a codebase, a program, that is separate from all the other programs. Thus, code repositories, often referred to simply as repos, are an archive of changes that have been made to the code base. What do you use a code repository for? Well, they act as a central place where you can store your code. And get a copy of the repository is stored on your local machine when you want to share it with others. You push the code to another repository and then access it. Repos also provide version control. They allow you to track the different versions of the software. It not only tracks the release version of the software, but it tracks the various development versions that were created along the way. With many people working on the same code base, the repository also provides tools that allow you to add your changes to the changes made by other data scientists. This is a process called merging. They also archive previous stages of code and related documentation. Code repositories are able to branch the code, meaning that they can create a copy of the code at some point in time. You get a localized copy of that is not affected by other data scientists' work. This allows for multiple data scientists to edit the code simultaneously and test their changes before merging them back into the main code branch. Code repositories have strong version control and collaboration capabilities that are critical for data scientists who are constantly compiling massive quantities of data. Git has the concept of committing code. It allows the data scientist to mark a point in time that they would like to save. Once they commit a code, they can always go back to that version. For example, you have developed an algorithm for a new machine learning model. It works, so you want to make sure that you can always go back to the working copy of the code. To do this, you commit your code to the repository. This creates a new version. Then you think of a way that you can improve the performance of the algorithm, and you want to try it out. So you make changes to the code. However, you realize that there is a fatal flaw in the design and it is not going to work out. No problem. Because you committed the previous working copy, you can always revert back to that version and ignore the changes you made. A similar process is used when you're collaborating on an analysis. Let's say you and your coworker decide that you're going to split the work between the two of you. So each of you branch from the same version of the repo. When you're done, you have two partial solutions to the analysis. Source code management systems allow you to merge the changes together to complete the analysis. As you can see, version control systems are very handy for collaboration. When it comes to version control systems, there are two main types: centralized and distributed. Centralized version control systems rely on a central server where developers commit their changes. An advantage to this is that they are simple to set up and provide admins workflow controls. Examples would be systems like Subversion, CVS, and Perforce. The other type is distributed. Unlike centralized versions, a distributed version doesn't have a single point of failure. Developers clone repositories on their distributed version control workstations, creating multiple copies. The advantage of a distributed version control system is things like you can commit changes while you're offline. They also tend to be more flexible in the way they work, and they allow for fast branching. Plus, they have no single point of failure. Some of the more popular distributed version control systems are Git, Bazaar, and Mercurial. For the data scientists, this is really a nice option, and that allows them to create a repository on a local machine without having to get permission to set something up on a central server. They can also use the repo to perform the analysis. When the project is finished, they simply archive the repo. However, the problem comes when they want to collaborate. If they want to share their work with another person, each person has to set up their system to allow the other person to connect and share changes. But this doesn't scale. For large teams, each person would have to do this for every person that they want to share with. Plus, when they wanted to share their change, they would have to connect to each peer and push their changes. To avoid these headaches, normally there is one node that is set up and everyone pushes their changes to that peer. When anyone wants the latest changes, they pull it down from that peer. So, in practice, distributed version control systems are not always fully distributed. Many teams opt for a hybrid system. For example, a team using Git, a distributed version system, but having a central peer configuration, a server for sharing. Let us talk about using Git in your data science workflow. Git is a version control system that allows you to track changes made to a set of files and allows you to revert to a previous version if needed. It is important to version control your code so that you can keep track of changes you have made as you work through your data science project. It is just as important to track other work products, such as your JupyterLab notebooks and reports. By using a version control system, teams can collaborate by having a repository of files that each team member can contribute to and add their work changes through the merge requests. As we've already stated, it's very important to have a system that actually tracks your work product for various input sources, especially when it comes to data science and building data models. Again, since Git is a distributed control version system, it is fast. Most operations are very fast because they are done locally. You can work offline. The two major exceptions are when you want to push your changes to another peer or pull changes from another peer to your repo. Git is also fault tolerant. Even in the hybrid configuration with a central server, you can share your work directly with coworkers if the central server goes down. Oracle Cloud Infrastructure Data Science has a Git extension in Jupyter Labs. The Git extension is a user-friendly add-on to Jupyter Lab that allows you to do basic Git operations with a point-and-click interface. You can access the Git extension in Jupyter Lab Notebook by clicking the Git icon on the left-hand side of the notebook or clicking the Git menu option. You can do things like create or clone a repo, push or pull changes to other peers, stage changes for a commit, and look at the difference between versions. It works with cloud-based hosting services such as GitHub, Bitbucket, GitLab, OCI code repository, and even your own Git installation. The extension provides a graphical user interface to manage the files you want to track. It allows customers to easily get version control on their notebook sessions. Let us discuss some basic terminology in Git. We have mentioned a few of these terms already, but I want to make sure that you understand them as they're important to understanding Git. A commit is a snapshot of the code in its current state. Each commit is identified by a secure hash algorithm, SHA ID. This is a unique 40-character label. You can also add tags to the commits, which make for human-readable labels. A commit creates another version of a repo, a point in time that you can go back to and use it to see the differences between versions. A repository, also known as a repo, is a directory that contains all the changes to your work. Normally, this is a single project, a library, analysis, or a report. It can be either local or remote and is a collection of commits. The working area is inside the repo directory. It has all the files that are related to the version of the project that you are working on. When you change versions, which is called checking out a commit, the files will be updated. When you are working in a notebook session, these files are stored on the local block storage. It is the working area that you create and modify the files you want to track and get. Git has a concept of staging. When you have created or modified a file, you are ready to commit it. You have to stage it first. Basically, you are telling Git what changed files you would like to create a new version of. Once you have staged all the files you've changed, you can commit them. Let us look at a Git workflow diagram to make sure we understood each part of the process. At the center of all of this is the Git version control system. Let's talk about the workflow of making a commit. In the working area, which is just the Git repo folder, you create and modify files. When you have gotten to the point that you want to make a new commit, you stage those files. When you stage them is up to you. Some people like to get a large part of the project done before they commit. I personally like to make commits each time I get something working. If I break something, I do not have to spend a long time recreating the work or unraveling what I did since the last commit. Commits are fast and not expensive, so I like to do them early and often. To stage your files, you tell Git what files you want to add to the commit. You might have files that have changed that you do not want to add right now, or there might be files that you do not want Git to track, so you wouldn't stage those. The next is to commit the stage files to the repository. You will have to add a short comment about the changes, and it will track who made those changes. This is very powerful as it helps you figure out what commit you want to revert to, but it also lets you know who made the changes. I find that personally helpful when I'm collaborating, as I can ask the person about the changes that were made. These changes are stored in the Git repo. Remember, the repo is just a directory for a project. It exists locally and is a collection of commits. You can share these changes with someone by pushing them to another peer or getting the changes by pulling them to your repo. In the data science service, you can create your own private code repositories in the OCI code repository. The OCI code repository is a Git-like service that acts as a central peer like Git or Bitbucket. However, it is securely integrated into OCI's access and identification management system. You can make commits, updates, branches, etc. The amount of storage that you are using is also visible in the console, and an OCID is assigned to each repository upon creation, so that you can edit the contents of the repo, clone the repo to another peer, delete repos that you no longer need, view changes that have been made. You can see all of the commits, browse the branches, and see the size of the repo. Within the data science service, you can also work with remote repositories such as GitLab, Bitbucket, and even your own Git repos. You can also connect external repositories such as GitHub to the OCI repository. This connection consists of a type such as GitHub, a name, and a reference to the secret in the OCI vault. This holds your GitHub's account's personal access token. When you define the external connection, changes to your existing GitHub repo are automatically replicated in the OCI code repository. To grant users permission to access the repositories and other resources, you have to create AIM policies. Once you have an OCI or external code repository, you can clone it using HTTPS or SSH keys to create a local copy, add or remove files, commit changes, and work with different branches of GitHub operations. Whereas Git is a version control system, GitHub is a cloud-based service that hosts Git projects. Here's a broad overview of the Git repo workflow for connecting. Using the SSH protocol, you can connect and authenticate to remote servers or services. With SSH keys, you can connect to GitHub without supplying your username and personal access token each visit. When you set up SSH, you will need to generate a new SSH key and add it to the SSH agent. You must then add the SSH key to the GitHub before you can use the key to authenticate. Let's walk through some of the major steps. First, we need to configure Git on your local machine. Generally, you just have to install Git and enter a few default values such as your name and your email address. You will also need to create a GitHub account if you don't have one. Then create an SSH key pair if you don't have one. There are two keys, a private and a public. Add the public key to GitHub. This will allow you to authenticate your local repo to GitHub. You will need a local Git repo and a remote GitHub repo. If you are starting from scratch, the best way to do this is to create an empty repo on GitHub, and then in the notebook session, clone the repo. We will talk about cloning a bit more, but basically it is a way of copying the remote repo to your local machine. Now it is time to get to work. You create your files, write your tests, write your code, commit your files to the local Git repo. Once you have changes that you want to share, you would push them to the remote Git repo. Pushing is the process of transferring the changes from the local repo to the remote one. Let's go over some Git commands. These commands all start with Git, followed by an action. Git initializes or creates a new repository or converts an existing directory or folder to a Git repo. You will need to give it the name of the repository. Git clone takes a URL to another repo. It then creates a local copy of their remote repo and links the two of them so that they can share commits. Git add takes a list of file names and stages these files for the next commit. Git commit makes a snapshot of the stage files. This creates a new version of the code that is ready to be pushed to the remote repo. Git remote has a number of uses. It can create, view, or delete connections between local repos and remote repos. Git fetch downloads commits files and data from the repo that's remote onto your local repo. Git push will upload local commits to the remote repo. Git pull is like Git fetch in that it downloads just changes from the remote repo. However, it merges those changes into the local repo such that the local repo has all the commits that the remote repo has. Let us review the key items that we have discussed in this module. We talked about what a version control system is and the different types, centralized and distributed. A code repository was defined and what it's used for. We also talked about why using version control systems is important for your data science workflow. You were introduced to the Git extension in the notebook session. Some Git terminology, such as commit, repo, working area, and staging, were defined. We also introduced the OCI code repository service and how it can be linked to external repos such as GitHub. You were shown the steps needed to set up a remote repo. And finally, we reviewed some of the common Git commands such as init, clone, add, commit, push, and pull. Thank you very much. Hello, my name is John Peach and I'm a data scientist on the Oracle Cloud Infrastructure data science team. The objective of this demo is to create a new local Git repository, commit files to the repository, clone the GitHub repo, and push some files back and forth. The first thing that we need to do is to configure Git so that we can authenticate. To do that, let's open a terminal. And Git is already installed, so we just need to configure it. So we're going to do git config user.name and my name. We're also going to do git config user.email. And what this is used for is when you make commits, Git will record who actually made the commit, so when you're sharing work, you can figure out who changed what. So we can check to make sure that this configuration is set up properly. We can do a config list, and it will list our settings, and there my name and my email is correct. So we want to create a repo locally. So what I'm going to do is I'm going to come over here to the file browser. You can get that by clicking here. I'm going to right-click, new folder. I'm going to call it demo. Then we can go down to the Git icon, and I'm going to say initialize repository. And I'm going to confirm that. And now we've got a Git repo. And we can see over here on the left-hand side, different Git-related tools. GitHub requires us to make authentication requests when we do pushes, when we want to change the data in the repo. So it does this through an SSH key pair. If you have an SSH key pair, you can skip this step, but what I'm going to do is I'm going to generate one. And the way we do that is we use the SSH keygen command. And then this option here tells it what type of key that I want. And I'm going to label it with my work address. So it asks me where I want to store it. I'll choose the default. Asks me for a passphrase. I'll just hit enter. And now I have that created. And we can check to make sure that there was 2 files created. So we're going to do that. Looking at the files that should have been created, we'll see that 2 files were created. This one here is your private key. This is what you have to keep secret so that nobody can access your account. And then this is your public key, and you can expose that to anyone. You can give it away. You can put it up on a website if you want. So let's take a look at what that looks like. It's just an SSH key, and at the end is my identifier for the key. So we want to copy this to the clipboard because we're going to need it in a few minutes. And now we're going to start the SSH agent that will track our keys for us. So we want to run it in the background. This is just something you have to do once. There we go. So now that's running, and I need to add the key that I just created to that agent. So we're going to use SSH add. We're going to go -k, and then we're going to point it at the private file, the private key. Great. that's been added. Now it's time to add the keys to GitHub. So if you go over to your GitHub account and click on your profile and go down to Settings, and then come over here to SSH and GPG keys, click on that, and then we want to click on New SSH key. And I'm just going to paste that public key into the box and click Add SSH key. And now we can see it showing up right here. Next thing we want to do is create a new Git repo. So I'm just going to go to this address, and I'm going to select the owner. But you may not have this option. It's a commercial option. And I'm going to give the repo a name, demo, and I'm going to come down here and say create repository. So that will create a repository for us. Right here, we have this address. Notice git at GitHub. There's different versions. There's an HTTPS version and an SSH version. With the SSH version, let's copy that. And then if we go back to our notebook session and go to Git, add remote repository, paste that in and go OK. Now the repo that we're in, that we created here locally, is linked to the repo that is up on GitHub. We can show that the local repo is linked to the remote repo by going into the repo and then doing git remote -v, and it lists that the origin is GitHub, and it's going to use that for fetching and for pushing. So let's go create a document. So if we come back into the launcher and we go File, New, Notebook, it's going to create a notebook. And we're going to see over here on untracked that this notebook is not being tracked by Git. So let's go ahead and track it. Now that it's tracked and it's staged, what we want to do is commit this. Let's commit this. So let's click this. And then we're going to enter in some message here. So I'm going to just say initial commit. And then scroll down and click the commit button. And it commits the changes. So let's push that up to the GitHub repo. And we can do that. First, we need to tell Git where we want the upstream to be. So we have to do, this is a one-time thing, the repo, is you do a git push set upstream origin. So this is where we want it to go. And then this is the branch that we want it to go into. So this is linking our current branch with the master branch on GitHub, which is called origin. So now we've pushed that up, and what we can do now is we've set that. We can go up to Git and say push to remote. That's pushing the changes up. It successfully pushed it up. Let's go back to GitHub and we'll see if the file is there. So we go on the demo and we see here's the file we committed, and this is the commit message. So let's come back and say we wanted to do some changes. We're going to sit here, I'm going to do some magical math here. We're going to run the code, and now we want to capture this and save the change. So I'll go over here to say File, Save Notebook, and then we'll notice that on the Git tab, it says that the untitled has changed, and since we're tracking it, and I'm ready to commit it, I'm going to right-click on it and click Stage. So now it's staged. I'm ready to commit. So I can put a Git summary in here. Let's say some math. That's what I did. And now I commit it. I can go back up to Git. I can push to remote. And then if I go back to GitHub and I reload this page, I'll see that the file is there and some math. So that has the latest changes. So in this demo, We configured Git, set up the repo, created an SSH key, and used that to link our notebook session to GitHub. Then we created a Git repo. We created a repo on GitHub, and then we linked the two of them together so that the notebook session and GitHub have the same files, and they can communicate back and forth. Then in the notebook session, we created a document, we staged it, we committed it, we pushed it to GitHub. And then just as a quick example of the workflow, we went and made some more changes, committed it, and pushed that up to Git. Thank you very much.
Welcome to the module covering the machine learning lifecycle. This first lesson is the overview of the machine learning lifecycle. I'm Wes Pritchard, Senior Principal Product Manager for Data Science and AI Services. When it comes to data science and machine learning, organizations want versatile and productive tools for their data scientists, and they want those tools to support the full machine learning lifecycle. Lifecycle like you see here in this simplified representation. The easier and more productive this life cycle is, the more valuable it is because it means the results of the life cycle can benefit the organization sooner and more frequently. In this lesson, we break down the process of building and managing machine learning models using 6 steps. The 6 steps you see here. So starting at the top, you have data access, data exploration and preparation, modeling, meaning model building and training, model validation, model deployment, and model monitoring, which can lead to refresh and eventually retirement. And the life cycle always starts with a business problem to provide an objective. Building a machine learning model is an iterative process. Many of the steps needed to build a machine learning model are reiterated and modified until data scientists are satisfied with the model performance. Incidentally, there are more complex depictions of the machine learning life cycle, such as CRISP-DM, which stands for Cross-Industry Standard Process for Data Mining, which you can explore more on your own if you want to. However, for the purposes of this course, this simplified life cycle works well, and we'll use this life cycle as a framework throughout this module to cover many of the activities of a data scientist must perform. In the rest of this lesson, we'll review these steps so we're all on the same page about what they mean. All machine learning models start with data. In OCI data science, it's advantageous to store data in the notebook session for quick access. Therefore, the first step in working a machine learning problem is accessing the data and collecting it into the notebook session. Because of this dependency on data, awareness of the data ecosystem in an organization can be advantageous to identify potential data sources. Data can come from many sources, and OCI data science has the ability to access many different sources. Typically, data scientists will obtain the data for the business problem they are working on by querying the data management systems where their organization stores their data. These enterprise data sets are usually heavily processed via data ingestion pipelines written by data engineers and ML engineers. These data sets typically reside in a data lake or in a database, whether relational or not. There may also be valuable unstructured data sets that don't fit well into a relational database, such as logs, raw text, images, videos, etc. The data catalog can be useful in finding data that exists in the organization. When data scientists don't have the data needed to solve their problems, they can get the data by using open source public data provided by many government entities, scraping data from websites, purchasing data from data providers, or collecting the data from surveys, clickstream data, sensors, cameras, and etc. After obtaining raw data, data scientists have to explore the data, visualize it, transform data, and possibly repeat the steps until it's ready for use in modeling. Data preparation is cleansing and processing raw data before analysis. Before building any machine learning model, data scientists need to understand the available data. Raw data can be messy, duplicated, or inaccurate. Data scientists explore the data available to them, then cleanse the data by identifying corrupt, inaccurate, and incomplete data and replacing or deleting it. In addition, data scientists need to determine if the data has labels or not. For example, if you have a series of images and you want to develop a detection model to determine whether there's a car in the image, you need to have a set of images where the cars are identified with bounding boxes and labeled as cars. If the training images lack labels, data scientists may have to label them themselves. Oracle provides OCI data labeling cloud service for this purpose. After data is prepared, data scientists explore the features, the variables in their data set, identify any relationship between the features, and make decisions about any additional data transformations. There are various tools data scientists can use for exploratory data analysis in open source libraries. A tool that performs statistical analysis of the data set and creates data visualizations to generate plots of the features is useful in this step. It's important to see what types of features are in the data set. After determining what kind of features there are, obtaining a distribution of values that each of the features has and getting summary statistics of each feature would be next. Doing so would help answer questions about the data, such as, is the data skewed toward a range of values or a subset of categories? What are the minimum, maximum, mean, median, and mode values of the feature? Are there missing values or invalid values, such as null? If so, how many are there? Are there outliers in the data set? During the data exploration step, it's helpful to plot the features and also plot the features against each other to identify patterns in the data set. This is where you can look for bias in the data. You also need to think about how will you handle outliers. Are some of your features correlated with each other? Do you need to normalize the data set or perform some other transformation to rescale the data, like log transformation? What's your approach to a long tail of categorical values? Do you use features as is, group them in some meaningful way, or ignore a subset of them altogether? During the data exploration step, you can identify patterns in your data set for ideas about how to develop new features that would better represent the data set. This is known as feature engineering. For example, if you have a traffic data set for the number of vehicles passing through a major intersection in every hour, you might want to create a new feature categorizing the hour into different parts of the day, such as early morning, mid-morning, early afternoon, late afternoon, nighttime. For categorical features, often it's necessary to turn a categorical feature into a binary feature, with one feature for each of the categories. Modeling or model building consists of choosing the correct machine learning algorithms to solve the problems and determining the features that go into the models. In the first step of model building, data scientists need to decide what might be appropriate type of machine learning model to solve the problem. There are two main types, supervised and unsupervised. Supervised learning involves modeling a set of input data to an output or a label. Classification and regression are supervised learning problems. Unsupervised learning involves modeling a set of input data without a label. For example, customer segmentation is an unsupervised learning problem. You don't need to know beforehand what customer segment a customer belongs to. A segment will be assigned by the model. Different classes of machine learning models are used to solve unsupervised and supervised learning problems. Typically, data scientists will try multiple algorithms and generate multiple model candidates. Data scientists don't know beforehand what model will perform best on the data set, so they experiment with several of them. During model training, a data scientist might experiment with selecting different subsets of features as inputs to the machine learning model. The benefits of reducing the number of input variables are reducing computational cost of model training, making the model more generalizable, and possibly improving model performance. During model training, the data set is split up into training and testing sets. The training data set is used to train the model, and the testing data set is used to see how well the model performs on data it has not seen. Once a trained model is obtained, it's important to evaluate the model to determine its suitability. There are many open source tools that help data scientists calculate the metrics needed for evaluating machine learning models and help them visualize the metrics. When evaluating machine learning models, data scientists need to decide which metrics are important for the business problem they're trying to solve. This is where the skill and knowledge of a data scientist is very important. For classification problems, one can use accuracy for model evaluation, but sometimes it might not be the optimal metric choice. If a problem involves detecting whether someone has a rare illness, a better metric might be how many people with the illness are accurately diagnosed divided by all the people with the illness. In that case, it would be more useful to look at a confusion matrix that shows the number of true positives, true negatives, false positives, and false negatives, and calculate precision and recall. For regression problems, you can use metrics such as root mean square error, mean absolute error, or calculate the coefficient of determination R-squared. For unsupervised problems, a set of clusters with high cohesion clusters is considered ideal. After the model training and evaluation processes are complete, the best candidate models are saved. Models are usually saved in Pickle, Onyx, and/or PMML format. OCI Data Science provides a model catalog for preserving models. Depending on the objectives, data scientists might work on a machine learning problem for proof of concept, experimentation, or to deploy it to production. Model deployment is the process of making the machine learning model available for use in some way. Most likely, the pipeline of data transformations have to be deployed also. Typically, data scientists will work with MLOps engineers on model deployment. Depending on how the output of the model is going to be consumed, it can be deployed for batch consumption or real-time consumption. For batch consumption, inferencing can be scheduled to run at predetermined intervals like every hour or every day. The result can then be stored in a data management system and consumed by other applications. For real-time consumption, a trigger would initiate the process of invoking the deployed model to serve a prediction. For example, deciding whether a transaction is fraudulent or not when payment is initiated requires real-time prediction. Considerations include how quickly a response is needed from the model. Is it milliseconds or seconds? The number of requests for the model and the size of data to be processed. Model monitoring is a challenging step, but important to make sure a model remains effective after it's deployed. Model monitoring helps the team decide if and when it's necessary to retrain the model and to redeploy. Model monitoring has two components: drift or statistical monitoring of the model performance and ops monitoring. After models are deployed, the metrics by which the models were evaluated may degrade over time. This is because the data can change over time. For example, features in the production dataset can exhibit values outside of the range of the training dataset, or there can be a slow drift in the distribution of the values. Because of potential model degradation, the quality of deployed models needs to be monitored. Sometimes it might take some time before it's clear whether a churn prediction model or a fraud detection model is providing an accurate prediction. However, it's possible to look at the statistics and distribution of the training data compared to the live data, and also compare the distribution of the model predictions with training and live data. Ops monitoring of the machine learning system will require partnership between the data scientists and the engineering team. Things to monitor include serving latency, memory and CPU usage, throughput, system reliability. Logs and metrics need to be set up for tracking and monitoring. Logs can be used to investigate specific incidents and help identify root causes. It's important to remember that machine learning is a very iterative process, and the steps outlined in this lesson can be repeated multiple times to achieve the business objective. In the following lessons, you'll see how OCI Data Science supports the data scientist in executing the machine learning lifecycle.
Hello and welcome to the next lesson in the Oracle Cloud Infrastructure Data Science course. My name is Himanshu Raj and I'm a data scientist and senior training lead for AIML at Oracle. In this lesson, we are going to learn about the first step in a typical machine learning lifecycle, that is to access data. We will be also talking about why we need data, how is it collected, and some of the key sources which we can use to access data in Oracle Cloud Infrastructure Data Science. Whatever we do, digital or non-digital, whichever app or service we use, we generate some information. This information can be categorized on the basis of size or source, usually as batch data, data from stream services, or application data. Batch data gets created over a period of time from daily workloads such as backups and data migration. Data from stream services, which are messages or logs from various user events and IoT devices. Application data is something which gets generated through API calls and come in form of application events, log files, and so on. We need to bring the data collected to Oracle Cloud Infrastructure for pre-processing and training our models. This data to be processed or trained on need to be accessible in data science, and this could be achieved through either by a user interface or through the command line with the help of certain libraries. So why we need data? Data science, being a multidisciplinary field, needs data to understand and extract insights. We need data to make hypothesis-driven research and conclusions, or to make data-driven research or conclusions. If we have a problem, what kind of data is needed to solve that? If we already have a ton of data, could we solve any of our existing problems? We will be now moving on to discuss some of the key sources from which we can access data in data science. We will discuss OCI object storage, local storage, Oracle Autonomous Databases, MySQL, Amazon S3, HTTPS endpoints, dataset browser, and PyArrow. We will discuss all of these one by one, but keep in mind, we are not only limited to these data sources. There are much more than just these which we can access data from. The first one is Oracle Object Storage. To load a data frame from the object storage, you can use the above example, replacing the angle bracketed content with the location and name of your file. Data can be accessed from Oracle Object Storage by either using API key or the resource principal, the latter usually being a serverless function. The setAuth module here enables or disables the resource principal identity or key pair identity in a notebook session. You can always refer to the ADS class documentation for any further information on these functions. Data from your local storage could be accessed by Pandas read CSV or similar function by defining the specific path as shown here. In case of autonomous databases, data science supports both of the Oracle Autonomous Database services. You can use ADS provided alternative functions, ads.readsql, which is 15 times faster than the generic Pandas readsql function. The reason being because it bypasses the ORM and is written to take advantage of being very specific for the Oracle Autonomous Databases. If you're using a database wallet file, you need to define the connection parameters along with the wallet location as shown here. You can then proceed on to read a SQL query with the help of ads.readsql method as shown here. When you want to access a database without a wallet file, you can do that by specifying the host name and the database port number parameters. You can see how it's defined in the connection parameters dictionary right here. But keep this in mind, this feature is only available with ADS version 2.5.6 or later. It's advisable to use bind variables because it helps you avoid the SQL injection attack. You can certainly refer more about it in the SQL documentation. Also, in case of data access from such databases, the performance is limited by various things such as network, latency, and so on. This response time from the database can be definitely improved by use of indexes or writing efficient SQL codes. OCI networking in itself is very fast, but still factors like VPNs and complex topologies can affect the performance. So you must factor in the time required to access the data. Again, to access the data from MySQL, you can follow the same steps as earlier, but you must remember to set the engine as MySQL. And keep in mind, this is also available with Accelerated Data Science version 2.5.6 or later. You can save the data frame to MySQL using ADS to SQL function, defining engine as MySQL, as shown here. So next we will talk about Amazon S3. So Amazon S3 public or private files can also be accessed in ADS via pandas. But for the private files, you must pass the right credentials through the ADS storage options dictionary. Data could also be accessed using HTTP and HTTPS endpoints, and you can access data via its URL using pandas library as shown here. In case of dataset browser, ADS provides this method to easily access datasets, well-defined datasets from reference libraries such as Seaborn, sklearn, GitHub, and so on. You can see the list of the supported libraries datasets using the list function as here. Again, you can explore them using open function by specifying the name of the dataset from a particular, the reference library. Oracle ADS also supports reading and processing big data into PyArrow by OCI file systems, or what we call it OCIFS library. This Pythonic file system holds connection information and allows typical file system style operations. So going on to the data types. So ADS detects the semantic data types automatically once we open a dataset. This could be categorical or qualitative, continuous, datetime type, or ordinal. Data can be categorized, that is labeled into different groups. That's the categorical one. For example, shirt size, eye color, these things. Without any quantitative value associated with it, it does not have an intrinsic ordering. For example, race. It can be categorized, but all races are created equal. Again, in case of ordinal data, it's an ordered category that has an intrinsic ordering. For example, education. Whether you have elementary, high school, undergraduate, or graduate, there is order there. In case of continuous, it's a type of quantitative data that couldn't be counted but measured, usually in form of fractions, height of a person, software release versions, and so on. And date times, as the name suggests, it deals with the datetime format. These semantic data types can be inspected by feature types and show in notebook functions. Moving on to the supported sources and formats by Oracle ADS. These are the supported sources and formats on the OCI data science via Accelerated Data Science Library. These are also listed in the documentation itself, which you can always refer. We support data from different sources and in various formats. We don't support text, doc, PDF, raw images, sequences such as list, tuple, range, and those kind of data. But we do provide a text extraction module to convert a PDF or doc into a plain text file. You can again read about it in the ADS documentation. Well, hope this was a valuable lesson on learning how to access data from some common sources in Oracle Data Science. Thank you. Hello and welcome to the next lesson in the Oracle Cloud Infrastructure Data Science course. My name is Himanshu Raj and I am a data scientist and senior training lead for AI/ML at Oracle. In this lesson, we will discuss about the second step in a typical machine learning life cycle, that is data exploration and preparation. All the data transformations and manipulations happens in this stage. We will be also discussing about the need for pre-processing and the steps involved in it. We will also learn about various ADS transformation built-in tools, as well as we will learn about splitting the data into train, test and validation sets using the help of ADS. So real world data, or the data we just accessed in the previous lesson, is generally full of discrepancies, sometimes incomplete or with several missing values. It could also have errors and outliers for that matter. So this generates the need to pre-process it before we start looking for patterns into it. The process involves various steps as per the problem we are trying to solve, as well as the data itself. We might use few or all of these steps involved for a particular ML use case. Also keep in mind that pre-processing is usually the biggest part in the entire ML lifecycle. So often is the case when data needed to solve a machine learning problem is from different sources and we need to combine them together. There are various row and column operations such as appending, deleting, filtering, which can be performed on the data to achieve the same. Also, all the operations that can be applied to a pandas data frame can also be applied to an ADS dataset object. In the later case of cleaning the data, it is very important to take care of formats, units, naming conventions to make sure the data is complete and there are no duplicates. This could also involve checking statistical summaries, data types, null values, and so on. We also need to join on columns, indexes, or we have to concatenate datasets either vertically or horizontally. Moving on to next step, which is data imputation. There might be missing data points in a real world data set, which could have been caused by human errors, such as wrong data entry or transmission errors. For example, when you have wrong GPS location recordings due to bad weather. Again, imputing takes care of these missing values. This process depends on the data itself, but usually achieved by either deleting the incomplete rows, which is least recommended, since it might lead to loss of valuable information. In that case, we fill the missing data with mean, median, or mode values for the entire feature column. For example, mode imputation might be a good candidate for categorical features. When dealing with nominal categorical data, ADS has built-in categorical encoder, that is label encoder module to enumerate categories into numbers. This converts the categories into numerical labels. But this might be a problem in case of ordinal data where hierarchy matters. One hot encoding takes care of this by transforming one categorical column with n categories into n or n minus 1 columns, which are dummy variables. We can achieve this by defining a function or by using pandas getDummies function. You can also encode all categorical columns using fit transform method. Coming on to outlier detection, an outlier might be an error or an actual observation. These observations sits far from the rest of the data and these don't represent the regular data that can be used for training. Outliers can be detected by visualization such as a scatter plot or box plot along with some statistical measures. The basic idea is that the normal samples or the true data points form a known distribution such as a Gaussian, and outliers are far from this distribution. Also, machine learning methods are the best suited for outlier detection. Identifying outliers is a classification problem in supervised learning. These are well suited if we have pre-labeled sample data, which again requires a huge precise manual effort. Unsupervised learning overcomes this challenge and is better suited in many cases. It does it by assuming that number of outliers is very small, in a proportion to the total sample data, and outliers don't fit the same trend as the normal samples. The next one is feature scaling. Feature scaling, as the name suggests, changes the scale of the features, or rather brings features onto the same scale. This is helpful, especially when where model is sensitive to the scale of the sample data. For example, one important feature is in order of 12, but another important feature is just in order of 1. These are widely used with algorithms using Euclidean distances, such as regression. There are two common approaches to achieve this. First one is normalization. Mean max is one such method where you squeeze or stretch all feature values in the range of 0 to 1, both included. The other one is standardization, also known as variance scaling, where you subtracts off the mean and divides by the variance. It keeps the mean to 0 and form a normal or Gaussian distribution, which is easier for model to learn weights. Dimensionality. Dimensionality refers to the number of features or input variables. Analyzing a high dimensional data is computationally expensive and hard to control. There are two ways to do dimensionality reduction. Either we select a subset of original features, which is called as feature selection, or we derive information from existing features to create a new feature subspace, which is called feature extraction. There are various methods to achieve both as listed here, but to discuss all of them is out of scope for this course. When it comes to text data, pre-processing could be little different than the numerical data and usually involves some or all of these processes, which are vectorized, removing stop words, POS tagging, tokenize, stemming, and lemmatization. ADS has built-in functions to transform and manipulate data. Any operation that can be performed on a pandas data frame can also be applied to an ADS dataset. Let's go over to the current built-in tools provided by ADS. First one is the suggest recommendations. When the suggest recommendations tool is applied, it shows the user detected issues with the data and recommends changes to apply to the dataset. You can accept the changes, and it is as easy as clicking a button in the drop-down menu. After all the changes are applied, the transformed dataset can be retrieved by calling getTransformedDataset. Alternatively, you can also use AutoTransform to apply all the recommended transformations at once. AutoTransform returns a transformed dataset with several optimizations applied automatically. It usually optimizes the dataset by imputing missing values in noisy data, dropping strongly correlated columns since they don't help its generalization, handling imbalance classes by either upsampling or downsampling, and by dropping constraint and primary key columns since they don't have a predictive quality. We will see some of these in the upcoming demo. Overall, autotransform is a very smart transformation tool which can fasten your work by a lot. The third one is visualize transforms. You can visualize the transformation that has been performed on a dataset by calling visualize transforms. It is only applied to the automated transformations and does not capture any custom transformations that you may have applied to the dataset. Here is an example of suggest recommendation use case where you can see the messages with related information such as strong correlations between features and another message showing imbalance target feature. You can also see variable names, suggested actions, and code to perform the said actions. This is really very helpful. Talking further about auto transform, all transformations results in a new dataset. It also has a fixed imbalance parameter which is set to true by default and helps with class imbalance by upsampling or downsampling the data. Next, you can see the flow diagram produced by visualized transforms in case of employee attrition dataset. The built-in function first prepares the data in this particular case, performs type discovery, and shows the recommended transformations. In this case, there were no feature engineering transformations. Keep in mind, the above results is dependent on a dataset and will differ on a case basis. Moving on to splitting datasets. Splitting dataset into train, test, and split is a very crucial step in a machine learning process. We do this to check how well our model is generalized and how the performance will be on an unseen dataset. By default, ADS splits the data to 80% for training, 10% for testing, and 10% for validation. Having a bigger testing and validation might lead to losing much of the valuable information. For larger datasets, training data to be 80 or 90% is fine, but we don't want the same in case of limited data. Maybe 70 or even 60% of the data as training set might be a better option, since very small test data don't provide a very good estimation of the generalization error. Here you can see how a data split has been done by defining dataset as well as test and validation sizes. Well, hope this was a valuable lesson on learning how to pre-process and split data in Oracle Data Science. We will go through a small demo now to have a quick hands-on. Let us now access a dataset and go through some pre-processing examples. The one I am using is employee attrition dataset and it contains 1470 rows. There are 36 features with 22 ordinal, 11 categorical and 3 constant values. The features include basic demographic information, compensation level, job characteristics, job satisfaction and other such employee performance metrics. The data is not balanced as fewer employees leave than stay. In the first cell, we are going to import all the needed libraries including the accelerated data science and pandas. You can see here that to load a data frame from object storage, we are using the resource principal method, which we have already talked about in our lesson. So, and again, we have defined the same in the setauth function. So moving on to dataset, to access the data in the OCI data science notebook session, we have defined a bucket, the namespace, and use the ADS dataset factory open method. So we have also defined our target feature as the attrition. The first built-in method is suggest recommendations. As the name suggests, it shows the messages with the data and recommended changes to apply to the dataset. You can see messages for different variables and suggested action along with the code. Alternatively, you can use auto transform to apply all the recommended transformations at once. Auto transform returns a transformed dataset with several optimizations applied automatically behind the scenes. You can visualize the transformation that has been performed on a dataset by calling visualize transforms. You can see the difference in case without running the auto transform, and this one is after running the auto transform. Before we talk about the categorical encoder, let's take the value count of job function feature from the dataset. We can see employees from the 3 categories here. ADS has a built-in categorical encoder that can be accessed from ads.dataset.label encoder. This example encodes the job function feature from the dataset, and now you can see instead of these categories, you can see the numerical values here. So again, you can also upsample or downsample your data as per use case. We are going to upsample using upsample method from ads.dataset.helper. So you can see here attrition being yes for this employee means he or she didn't stay. On further checking, after running the upsampling cell, you can see the data was upsampled now. So, and you can see the repetition of this particular name these many times. You can also go ahead and compare the attrition value counts now and compare it what it was before. So you can see the data has been upsampled. These are just few of the examples which we went through. ADS can really cater more scenarios. Again, once all the data transformations are complete, you can split the data into a train and test, or a train, test and validation set. The defaults, as you know, are set to 80% data for training, 10 for testing and 10% for validation. So this concludes our demo. You can refer the ADS documentation as well as our GitHub labs for more information. You can also refer to the notebook sample examples from the data science notebook session. We will see you in your next lesson.
Hello, I'm John Stainsby. In this lesson, let's learn about data visualization and profiling. Data visualization is an important component of data exploration and data analysis in modern data science practices. It is one of the initial steps used to derive value from the data. It allows analysts to efficiently gain insights from the data and guides the exploratory data analysis, or EDA. An efficient and flexible data visualization tool can provide lots of insights about the data for data scientists. Data visualization, or DV, is the presentation of data to illustrate findings and explain results. DV is essential for analyzing data and making decisions based on that data. It allows people to quickly and easily see and understand patterns and relationships, and no specialized training is required to interpret what's presented in the graphics. Most data visualization tools are capable of connecting with data sources like relational databases. This data, which may be stored on premises or in the cloud, is retrieved for analysis. Users can then select the best way to present the data from numerous options. Some tools automatically provide display recommendations based on the type of data presented. Consider a self-service tool that incorporates artificial intelligence and machine learning into the analytics to make certain tasks easier, particularly for users who are not analytically savvy. Your data visualization tool should have pre-built connections to load and integrate data from a wide variety of sources, making datasets easy to blend and helping you quickly decide what really matters. It should be designed so that it can be accessed across your enterprise and shared with your co-workers anytime, anywhere. With some projects, you may want to do everything yourself. With other projects, a little or a lot of automation may come in handy, so go with a data visualization tool that offers the flexibility to easily switch between human and machine. Look for ease of use, for example, point and click or drag and drop features, as well as capabilities to see your data visualized automatically, save you from doing those tasks manually. You want a tool that lets you quickly and easily add information or make edits, such as changing layouts to present new insights. An efficient and flexible data visualization tool can provide a lot of insight into the data. ADS provides a smart visualization tool. It automatically detects the data type and renders the plots that optimally represent the characteristics of the data. With ADS, custom visualizations can be created using any plotting library. Within the data science service, common visualizations are made easy through ADS. It offers automatic visualizations that help data scientists get fast and efficient insights. Smart charting automatically detects the data type of your columns and generates summary statistics, distribution charts, co-correlation maps, and anomalous data profiles, for example, data with a large number of missing values or high cardinality. Let's take a closer look at the following ADS automatic visualization methods. Core, or correlation. Show in Notebook, which is used in many classes within ADS. It makes a best effort to display information that's meaningful to a data scientist about the object. Plot, which is an automatic plotting tool. and feature plot, which creates custom visualizations. To visualize the correlation, call the showCore method. If the correlation matrices have not been cached, this call triggers the core function, which calculates the correlation matrices. Correlations are displayed independently because the correlations are calculated using different methodologies, and the ranges may not be the same. Consolidating them into one single matrix could be confusing. Continuous uses the Pearson correlation coefficient method. It is a measure of linear correlation between two datasets. The correlation range is from -1 to 1. Continuous categorical uses correlation ratio. It's a measure of the curvilinear relationship between the statistical dispersion within individual categories. The correlations range from 0 to 1. Categorical uses Kramer's V method. It's a measure of association between two nominal variables, which gives a value between 0 and 1. You can apply the ADS show in notebook method on a dataset. This creates a comprehensive preview of all the basic information about the dataset. This includes the type of the dataset, whether it's regression, binary classification, or multi-class classification, the number of columns and rows, feature types of each column, visualizations of each column, and the correlation map and a short dataset header. To improve plotting performance, the ADS show in notebook method uses a sample subset of the dataset. This sample dataset is a smart sample, calculated to be statistically significant within the confidence level of 95 and the confidence interval of 1. If you are interested in exploring the relationship between two columns, you can use the plot method. The plot method is an automatic plotting tool. You pass in a variable for the x-axis and optionally a variable for y, and then call the show in notebook method to plot. The type of plot that ADS generates depends on the type of columns, which is detected automatically through type discovery. Here are a few examples of the plot method in use. Passing only the x variable, attrition, which is of a categorical type, the plot method detects that the data in this column has either a category of 0 or a 1, whereas plotting a continuous data type results in a histogram. If you look at this violin plot, plotting column 2 against column 1, where one is a categorical type and the other is of a continuous type, ADS chooses the best plotting method to be a violin plot. In this Gaussian heat map, plotting column 1 against column 3, which are both of a continuous type, ADS chooses the Gaussian heat map to be the best way to visualize this data, and it generates a scatter plot. The feature type system allows data scientists to separate the concept of how data is represented physically from what the data actually measures. It extends Pandas data frames to store properties and methods for working with the feature. It uses multiple inheritance to define different characteristics of a single feature, and uses a warning and validation system to give you confidence in the quality of your data. The feature type system in ADS provides plots for all ADS-supported feature types. However, it's easy to create feature plots for your custom feature types. Calling feature plot on a Pandas series produces a univariate plot. Calling it on the entire data frame returns a data frame where each row represents a feature. ADS provides you with a good set of options to plot the columns of your dataset. The Visualization API is flexible enough to let you customize your charts or choose your own plotting library. You can use the ADS call method to select your own plotting routine. The call method allows users to have a more flexible way to plot using their preferred plotting libraries or packages. In this example, a data frame is passed directly to the Seaborn pair plot function that plots a pairwise feature relationship for the dataset. The function creates a grid of axes so that each variable in the data is shared in the y-axis across a single row and in the x-axis across a single column. The diagonal axes are treated differently, drawing a plot to show the univariate distribution of the data for the variable in that column. In this example, a data frame is passed directly to the matplotlib function. And in this example, we use public domain California earthquake data which gives a brief visual overview of major places where earthquakes have happened. In this lesson, you should have learned how to produce data visualizations, automatic data visualizations, as well as customized data visualizations. Thank you. Hello, I'm John Stainsby. In this lesson, let's learn about model training. Model training is a critical part of the modeling phase of the machine learning lifecycle. Let's first discuss what the model training process does. Model training builds the best mathematical representation of the relationship among features and a target label, in the case of supervised learning, and among all features in unsupervised learning. The model training process creates an artifact which captures these relationships or patterns. The process determines the best algorithm for training, considering a large number of dimensions. This flow diagram is a representation of the typical steps performed during model training. There are a few functions at play here. The model has a score function indicating the fit of the model. This might be an error function or a maximum likelihood function. The loss function, also known as the cost function, compares the predictions made by the model to the true target values in the training dataset. The objective of the loss function is to represent the difference between the predicted values and the true target values as a single number, the loss score. The graph on the right represents this process, as the green dots are the true data points, the black line through the middle represents predictions, and the red arrows represent the loss. An update function updates the parameters of the fitted model from one iteration to the next. In the software world, open source refers to freely and publicly available source code that can be modified as well as redistributed. Open source frameworks are easy to access and have large community support, which helps in driving new innovation and quickly solving existing bugs to tackle new business challenges. Our data science environments provide a perfect mix of Oracle proprietary and open source frameworks. They can be leveraged together to target various business and research use cases. A few of them are listed here on the screen. You can also install any external library by using a terminal in any existing environment if needed, or you can just start with a set of your own choice of libraries and frameworks. Model training can be done in a number of ways. Via notebooks, by writing and executing Python code in the JupyterLab interface. Via the data science Conda environments with the help of ADS, MLX, or AutoML, which we will be discussing in detail later in this module. Or via jobs, which we'll cover in Module 4. In this lesson, we've covered what the model training process is, and that our environments leverage Oracle and open source frameworks as well as your own to train models. We've also covered a brief introduction into the various ways to train models. Thank you.
Congratulations on reaching so far in the data science course. My name is Himanshu Raj and I am a senior training lead for AI/ML at Oracle. In this expert tip video, I will talk about training a ML model on OCI. And so basically you can easily train a simple ML model using jobs from the data science service, as I mentioned. And again, you may use GitHub to host the source code and use OCI object storage to store the results. Using ADS, you can create a job to define the resources and a job run to source the training code and save the training output. Again, you can do this either with Python code and YML file. So the next thing which I want to talk about is distributed training on the OCI. So again, to allow horizontal scaling to parallelize training tasks for large data sets or compute intensive workloads without compromising with the training time or model accuracy, you can do distributed training with OCI data science service with the help of ADS. Again, we support well-known frameworks such as Dask, PyTorch distributed, Horvath, TensorFlow distributed. I would again advise you to go through this documentation and details and to implement some distributed training use cases on your own. Again, you can share the same on the GitHub and post that in the OU community. Also, you can choose either Docker or GitHub for these implementation. So if you'll go through each of the subsections, you will find the further details to how to do the implementation for each of the framework. Other than these, we have also covered AutoML in our course. I will also advise you to go through the AutoMLX package, which is available in the OCI data science service in the AutoMLX Corner pack. The Oracle AutoMLX solution provides a pipeline that automatically finds a tune model given a prediction task and a training dataset. Again, you can either choose a Dask or a local as the parallel engine with the init function. So again, please go through the ADS documentation as well as the ADS class documentation. So you can find the class documentation right here. Again, keep an eye on our release notes as well as new features which keep coming, and please post and discuss your work in the OU community. Thank you for watching this video.
Hello, I'm John Stainsby. Let's learn about building and training with AutoML in Accelerated Data Science, or ADS for short. AutoML stands for Automated Machine Learning. In the modeling phase of the machine learning lifecycle, multiple models are built using a variety of algorithms and with different hyperparameter configurations. Performance and accuracy of these models must be tracked. This whole process can be automated, which is where, as the name implies, AutoML comes in. Machine learning is an art that requires lots of iterations and experimentations. It's rare to have an optimal model with optimal set of hyperparameters in the first iteration, which provides an opportunity for AutoML. AutoML combines the process of choosing and refining models, tuning parameters, and hence optimizes the outcome of the learning. There are a few AutoML approaches. Bayesian optimization uses a probabilistic model to capture different hyperparameter configurations and their performance. AutoSKLearn, one of the most notable works relying on this approach, adopted a random forest-based sequential model-based optimization technique for general algorithm configuration. It uses meta-learning to identify a previously optimized dataset closest to the given dataset, and uses the known dataset's configuration to bootstrap the iterative optimization process. A second class of solutions frame the AutoML problem as a recommender system, where the system maintains a record of the best configuration found for each dataset it's previously encountered. Given a new dataset and the results of several initial trials, the system uses similarity to known datasets and configurations to suggest the next configurations to evaluate. Probabilistic matrix factorization is typically at the core of recommender systems. A third approach relies on genetic evolutionary algorithms. One notable example is the tree-based pipeline optimization tool, or TPOT for short, which automatically optimizes a machine learning pipeline built around scikit-learn. All three approaches require multiple iterations to produce a model. Instead, we use a non-iterative approach to predict relative algorithm performance throughout the pipeline, improving efficiency compared to sequential and iterative approaches. Oracle AutoML is designed to provide accurate models in a shorter runtime. In our feed-forward approach, each pipeline stage makes decisions based on meta-learned proxy models that can predict candidate pipeline configuration performances before building the final model. It then builds and tunes only the best candidate pipeline. Additionally, previous approaches have a known issue called the cold start problem, which is to say the inability to predict how a pipeline configuration will perform on a brand new dataset. This is avoided by leveraging meta-learning, where different pipeline configuration behavior is learned on a wide variety of datasets. We use this to obtain hyperparameter configurations for our proxy models, which our pipeline uses to estimate relative performance of every algorithm and make decisions based on these estimates. Oracle AutoML also provides the ability to undertake a full machine learning cycle without the user having to write any code at all. It automates the process of selection and tuning. Users can feed a dataset to AutoML and it will train multiple machine learning models, tune the hyperparameters for those models, and evaluate their performance against each other. AutoML can improve the productivity of data scientists by automating the training process and avoiding tweaking every aspect of the model training. It also reduces the compute time that's required to deliver ML models. Oracle AutoML automates the workflow and provides you with an optimal model given a time and budget. A typical workflow is: select a model from a large number of variable candidate models. For each model, tune the hyperparameters. Select only predictive features to speed up the pipeline and reduce overfitting, and ensure the model performs well on unseen data, also known as generalization. Oracle AutoML automates 4 major time-consuming and tedious steps in the machine learning process to deliver significant productivity improvements for data scientists. Algorithm selection identifies the best algorithms for the data and problem. Adaptive sampling identifies the right sample size and adjusts for unbalanced data. Feature selection denoises the data and reduces the number of features. And finally, model tuning auto-tunes hyperparameters for the best model accuracy. Let's look at each of these in more detail. Given a data set and a prediction task, such as classification or regression, the goal of algorithm selection is to identify the algorithm that yields the maximum score. This best algorithm is not always intuitive, and picking complex models is not always optimal for each use case. The ADS algorithm selection stage is designed to rank algorithms based on their estimated predictive performance on the input dataset. Using models built from a wide range of datasets, automated algorithm selection uses meta-learning, where, based on the distribution of values or meta-features in the data, a pre-built model predicts which algorithms are most likely to produce the best results. Algorithms with the highest scores are later used for model tuning. This helps data scientists and non-expert users find the best algorithm candidates faster than with an exhaustive search. Adaptive sampling iteratively samples a dataset from a small subset to the full dataset size and evaluates each sample to obtain a score for a specific algorithm. The goal is to find the smallest sample size of a dataset for use in a subsequent pipeline stage without sacrificing the quality of the pipeline. It also detects unbalanced datasets that can cause poor models to be built. For a given algorithm and dataset, it identifies a sample based on the sample size and characteristics of the dataset and task. It leverages meta-learning to predict algorithm performance on the given sample. It iterates until the score converges to within a small threshold. The identified sample is then used for subsequent stages of the AutoML pipeline. This stage selects a subset of features that are highly predictive of the target. Attributes that have no correlation with the target attribute, have too many constants or missing values, or have too high a cardinality can reduce model quality, while increasing the model building and data scoring time. AutoML first ranks the features and evaluates subsets based on these rankings, using several techniques, and automatically removes those attributes that contain little information, or worse, noise. For a given dataset, obtain dataset meta-features similar to those obtained in model selection. Rank all those features using multiple ranking algorithms. This creates multiple feature rankings, which are essentially ordered lists of features from the most important to the least important. For each feature, the optimal feature subset is identified, and the algorithm performance is predicted by leveraging meta-learning on a given feature subset. Iterating over multiple feature subsets, the optimal subset is determined. This is the final stage of the AutoML pipeline. It determines the optimal configuration for the model's hyperparameters. The hyperparameter tuning process is designed with efficiency and scalability as first-order requirements. AutoML performs model tuning for each selected algorithm to find hyperparameter settings that significantly improve the model, but without resorting to exhaustive search. For example, in a decision tree, AutoML explores and optimizes the maximum tree depth and minimum split percentage for the algorithm. Oracle AutoML Provider delegates model training to the ADS AutoML package. It supports two arguments: n_jobs, which allows you to specify the degree of parallelism, the default is -1, which means all cores are used, and log level, which allows you to control the verbosity of the output. You can visualize results at each stage of the pipeline. The Oracle AutoML process provides summaries, including training data information, pipeline information, and model trial information. Note that adaptive sampling will not run if there are fewer than 1,000 data points. Use model_list to control which algorithms AutoML will consider during optimization. You can also specify your own score metric from a list of metrics. The defaults are ROCAUC for binary classification, recall macro for multi-class classification, and negative mean squared error for regression. AutoML supports a user-supplied time budget target in seconds. It will attempt to terminate computation at that time and will return the current best model, depending on which stage in the pipeline termination occurred. You can use a minimum feature list to ensure that features are not dropped during feature selection. In this lesson, you should have learned what are the advantages of ADS AutoML. We looked at the AutoML workflow and pipeline. We also learned about how an algorithm is selected, how adaptive sampling is done, and how a feature is selected. We also saw how model tuning is done. Thank you.
Hello and welcome to the demo, building a classifier using AutoMLX. So in